Okay, welcome back. We're doing a deep dive today looking at this fascinating material you brought in on quantum computing.
Right.
And our goal here really is to pull out the core ideas,
hmm
uh, understand what makes it genuinely revolutionary, and look at the potential, but also, the real challenges too.
Yeah, and I think the material makes it clear right away that the big shift is away from classical computers. We're all used to bits, just 0 or 1.
Simple on or off.
Exactly. But quantum computers, they use qubits. And the research really emphasizes this quantum mechanics aspect. Qubits can be 0, 1, or kind of a mix of both at the same time. That's superposition.
A blend, not just one or the other. And this isn't just theory, right?
Mhm.
The source is stress. This allows for, well, it's like massive parallel processing.
That's a good way to put it. It's like checking many possibilities simultaneously, not just one after the other.
Okay.
And that's where the exponential power comes from. Some of these reports talk about problems that would take today's best supercomputers, like millennia. A quantum computer could potentially crack them in minutes, maybe even seconds. It's just a whole different scale of computing.
And that must be why we're seeing these huge investment numbers you highlighted. Forecasts hitting, what, over $100 billion by 2040?
Yeah, that kind of money shows this isn't just a lab experiment anymore. It's seen as serious, potentially transformative technology, big economic implications down the road.
So beyond superposition, what else is key? The material mentions entanglement.
Ah, yes, entanglement is, well, it's almost spooky, like Einstein said. You link two qubits, and they share the same fate, the same state instantly, no matter how far apart they are.
Okay, that is weird. And interference.
Interference is more about how the algorithms work. You sort of nudge the quantum waves, amplifying the path towards the right answer and canceling out the wrong paths. Like noise cancellation, but for computation.
Got it. So putting this power to work, where did the sources see the biggest impacts? Cybersecurity comes up a lot.
Definitely. The power to break current encryption is a major concern, but also the potential to create new, theoretically unbreakable quantum encryption.
A double-edged sword. And simulating molecules. That seems huge for, like, drug discovery.
Yeah.
New materials.
Oh, absolutely. Classical computers really bogged down trying to simulate complex molecules accurately. Quantum computers could potentially model them perfectly. It's like having the ultimate virtual chemistry lab.
And the material also mentioned AI, speeding up machine learning.
Yeah, handling enormous data sets, training models that are just too complex. Right now, that's another big area of hope.
And optimization, too. Things like logistics, supply chains, finding the best route, the best plan.
Exactly. Those messy real-world problems with tons of variables, quantum might offer shortcuts to optimal solutions that are currently out of reach.
Okay, but let's talk hurdles. The material doesn't shy away from them. Qubit fragility seems like the big one.
It really is. They're incredibly sensitive. Any little bit of noise, heat, vibration, stray magnetic fields can make them lose their quantum state. That's called decoherence.
And decoherence means errors.
Lots of errors,
Mhm.
which is the central challenge right now. And fixing errors isn't easy. You need, like, potentially thousands of these fragile physical qubits just to build one stable, logical qubit using complex error-correcting codes.
So the engineering and the cost to scale that,
Right.
it's massive.
Immense. Which leads to this term the research uses, NISQ, noisy intermediate scale quantum.
Right.
We have machines now, maybe dozens, hundreds of qubits, but they're noisy, they make errors, they aren't fault tolerant yet, so the useful problems they can solve today are still pretty limited.
So everyone's racing towards fault-tolerant machines
Yeah.
and achieving quantum advantage, which means
It means actually solving a useful real-world problem faster or better than any classical computer could. Not just a theoretical demonstration, but something practical. That's the next big milestone everyone's chasing.
okay, so stepping back, summarizing this deep dive from the material, quantum computing, it's this revolutionary jump using superposition, entanglement, interference.
Right, offering potentially exponential power for certain really hard problems.
Huge promise in medicine, materials, finance, AI, breaking and making codes. But
But balanced by these major, immediate challenges. Qubit fragility, noise, errors. The huge engineering task of building fault-tolerant systems. That defines this current NISQ era.
it's this fascinating mix of incredible potential and really tough engineering problems to solve.
Precisely. The race is definitely on.
Which brings us to a final thought, something for you to think about, drawing from all this potential impact we've discussed. If quantum computing really can reshape whole industries, national security, maybe even help with global challenges, how do we make sure this quantum revolution doesn't just create more inequality, How do we aim for something like quantum justice, making sure the benefits and access are shared broadly, not just concentrated?
That's a crucial question to keep in mind as this all unfolds.
Definitely something to reflect on.